Hello, friends. Welcome to Science Talk. I am your host, Jim Massa. I want to discuss with you what we see here. Increased rainfall stimulates permafrost thaw across a variety of interior Alaskan boreal ecosystems. Now, this is a very lengthy article, so I am not going to go through this in detail. I will, in the comments section below the video, not in the description box, but the comments section, I will post this URL so that you can click on it and then examine this in detail at your leisure. So, what's going on here? And this is kind of related to a video, well, at least the concept of a video I did some time ago of how there's been more winter rains that add to the increased melting of Greenland's ice. So we're seeing a similar thing here where we're basically thawing out the permafrost. So we're warming the Arctic, so we're having, instead of snow, we're having liquid precipitation, and this is increasing melting of ice, increasing thawing of the permafrost. That's the general idea here. Okay. So here are the researchers there: Thomas Douglas, Merit Turetsky, and Charles Coven. Okay. Abstract. So this is a typical scientific paper. Abstract, intro, methods, results, discussion. Although a trend I've been noticing lately is that the methodology is now placed after the discussion at the end. Be that as it may. Earth's high latitudes are projected to experience warmer and wetter summers in the future, but ramifications for soil thermal processes and permafrost thaw are poorly understood. Here we present 2,750 end-of-summer thaw depths, representing a range of vegetation characteristics in interior Alaska measured over a 5-year period. This included the top and third wettest summers in a 91-year record and 3 summers with precipitation close to mean historical values. Okay, now comes the nub of their findings. Increased rainfall led to deeper thaw across all sites, with an increase of 0.7 plus or minus 0.1 centimeters of thaw per centimeter of additional rain. Disturbed and wetland sites were the most vulnerable to rain-induced thaw, with approximately 1 centimeter of surface thaw per additional 1 centimeter of rain. Basically, what they're saying here is that the rain is of sufficient temperature and the rain is of sufficient amount that is percolated through the ground and it maintains the above freezing heat content so that it can then thaw the ground out below and basically start worming its way down, if you will, deepening the thaw layer, in essence, is what's being found. So instead of like, we go down 20 centimeters and we hit the frozen layer, the frozen layer is thawing, so now we can go down 23, 25 centimeters, and so forth. That's the general idea. Permafrost in tussock tundra, mixed forest, conifer forest was less sensitive to rain-induced thaw. A simple energy budget model yields seasonal thaw values smaller than the linear regression of our measurements, but provides a first-order estimate of the role of rain-driven sensible heat fluxes in high-latitude terrestrial permafrost. This study demonstrates substantial permafrost thaw from the projected increasing summer precipitation across most of the Arctic region. Remember, as I discussed in my ocean heat content video, sensible heat is heat that's added to a phase to increase the temperature. So you have liquid water, you add heat to liquid water, you increase the temperature. You have gas, you add heat to the gas, you increase the temperature. Latent heat is the heat added to or subtracted to change phases, solid to liquid, liquid to gas, or the other way, gas to liquid, liquid to solid, in which case heat is removed. Right? So when you're going from solid to liquid or liquid to gas, you're adding latent heat energy. To go the reverse direction, you are removing that latent heat energy. Okay, go through some of the introduction here. Arctic amplification has caused enhanced warming in Earth's polar regions compared to lower latitudes. Commensurate with this are projections for a year-round increase in precipitation that is expected to be greater than at lower latitude locations. Recent studies have already reported increased summer wet precipitation in the Arctic. That means non-snow, and this is projected to continue in the future. The fraction of wet, liquid, to dry, snow, precipitation is also projected to increase as the summer season lengthens. Increases in projected Arctic summer precipitation are largely under high emission and warming scenarios than for lower emission scenarios. It is clear that increased Arctic summer precipitation will influence hydrologic processes and the soil thermal regime of the permafrost that underlies 24% of the northern hemisphere. Permafrost soils contain large carbon stores, twice what is currently in Earth's atmosphere, and permafrost, when kept frozen, provides stable ground surface conditions for infrastructure. Increased rainfall has recently been linked to methane release from thawing soils. Changes in snow conditions and liquid water are known to affect the permafrost thermal state, though some aspects of heat transfer, this is the latent heat now, are better understood than others at advective heat transport. Most of the studies linking precipitation and permafrost thaw have focused on increasing winter snowpack that provides thermal protection against winter cold. Relationships between the depth of the seasonally thawed active layer and increasing rainfall have been documented in a few studies, but how these relationships vary over time, space, or changing precipitation regime in northern ecosystems is poorly understood. Translation: that's what we're doing here. Okay. Now, so as you can see here, there's when we think about the permafrost thawing and the methane being released as the organic material is acted upon by microbes, we're always thinking of the warming temperatures of the atmosphere, which of course is important. Here's something else you probably, I bet most of you have probably not considered. What precipitation, wet precipitation, how that impacts. If you start, the wet precipitation is percolating through and is helping to thaw out the permafrost along with the warming temperature. That's another mechanism for further release of methane. And if the precipitation patterns are changing, which we are seeing, so we're getting more of the rainfall as opposed to the snowfall, along with the warming temperatures, that's yet another positive feedback mechanism to increase, further exponentiate carbon release into the atmosphere. Okay. In permafrost terrains, the seasonally thawed active layer depth is controlled by local climate, vegetation, soil properties, hydrology, topography, timing, then thermal conductivity of the previous winter season snowpack. In terrains with near-surface permafrost, the seasonal thaw front moves downward throughout the summer, so the end of summer season surveys represents the maximum active layer extent. The seasonal thaw layer is referred to as the active layer. And then below the active layer, you have, that's when you hit the permafrost that stays frozen year-round. Most of the studies linking vegetation to permafrost thermal protection have focused on the thermal conductivity or albedo of the vegetation represented. In other words, is the vegetation, does it have dark leaves or lightly colored leaves? Darker leaves will absorb more sun energy than lighter leaves. By fire or human activities, provide the least protection against surface thaw. A key knowledge gap remains in our ability to project how and where these surface properties regulate the sensitivity of permafrost to changes in the type and amount of precipitation. Here we explore the relationship between anomalously wet summers and thaw depth using 2,750 end-of-summer active layer thickness measurements at a variety of locations in discontinuous permafrost near Fairbanks, Alaska. Woohoo! Anyway, discontinuous permafrost means that if you were to go into the ground and you drill down, in some locations you may hit permafrost, other locations you will not. So the permafrost is discontinuous. When you go further north, for example, north of the Yukon River, up towards the Brooks Range, the permafrost will be continuous. In other words, no matter where you drill down in the ground, you're going to hit that frozen layer. In some places, especially in the boreal forest region, everywhere you drill down, you're not going to necessarily hit permafrost. And the clue as to, if you will, is to look at the trees. If you got short little black spruce trees, chances are you got permafrost underneath them. But if you're seeing birch trees and poplars, trees that require deep roots, chances are you're not going to find permafrost underneath the ground in those areas. So you can see you got a stand of spruce transitioning to a stand of birch trees. Well, probably got permafrost under the spruce, but not under the birch trees. It would be discontinuous. So they looked at various vegetations: tussock tundra, black spruce with sphagnum, mixed deciduous forest, wetlands, and disturbed areas. Okay, so here is basically where some areas of where studies and measurements were taken. This is not pronounced creamer; it's pronounced Kramer. This is Kramer's Field Refuge. This is now basically a protected area. Every year, we get migratory birds that come into this region. Get the cranes, sandhill cranes. You get the geese, various ducks, etc. You can see here, this is residential. This is right off what's called College Road. UAF is like just this way. Seriously, it's like about 3/4 of a mile this way. And I live way out here. So if you extend the map out. The permafrost tunnel is a really cool place. It's a tunnel, and you go in there and you see the permafrost. And it's an active research site, as well as tourists can go there. I think they can go there. We might need special permission. And the Farmers Loop transects. Basically, this road that you see here is that's Farmers Loop Road. But this is College Road, and you get to some, like Old Stees Highway, blah, blah, blah. But this is a well-protected area. It's a really cool spot. There's all sorts of different types of ecosystems in there. It's one of my favorite places to go to. I will actually bike there to my house, which is about, was probably like a 15-mile bike ride one way. And just look at the birds, go exploring. Really cool spot there. So as you can see here, this length here is about 3 kilometers, and so on. Oh, they describe here the measurement period, when they did it, how they did it, and so on. As I said, this is detailed. I'm going to leave the link in the comments below the video. You can then click on the link and read in detail for yourself. But what I want to go through is what they're showing here. So it looks like the years are out of order, 13, 17, 15. But what they're doing is they're ranking it from driest up here at the top to wettest down here at the bottom. Okay? So they looked at, in red, 24-hour wet precipitation totals for April 20 through October 10 for the years 2013 to 2017, measured at the Fairbanks International Airport. Numbers correspond to rankings of the 100 largest 24-hour wet precipitation total. The black lines are the cumulative wet precipitation for that season. Okay? So, what do we have on the vertical axis? On the right side, we have the cumulative precipitation in centimeters, in 5-centimeter increments. On the left side, we have 24-hour wet precipitation in centimeters. So, 2.5 centimeters is an inch. Okay, so as you can see, we had a couple of them. This is pretty dry here. Not much happening there. Not much happening there. So they rank them from driest to wettest. And as you can see, we had some pretty wet stuff going on here in 2014. So that's what this is basically indicating. Wet from the driest to the wettest. Okay. Results. Increased summer rainfall led to enhanced permafrost thaw across all 5 ecotypes. That's figure 3. We'll go through that in a moment. For example, the maximum active layer depth was closest to the surface in the driest summer, 2013, was considerably deeper in the 2 anomalously wet years of 2014 and 2016. Across the entire measurement period, increasing rainfall led to an average of a 0.7 plus or minus 0.1 centimeter increase in active layer depth per centimeter of additional precipitation. The wet summers led to a steady increase in active layer depth between 2013 and 2017. Following the extreme wet summer of 2014, it was wet, let me tell you. Thaw depths did not return to 2013 values despite summers of 2015 and 2017 being similar in air temperature and wet precipitation totals. In addition, following the anomalously wet summer of 2016, the 2017 thaw depths were only slightly shallower despite temperature and wet precipitation values in 2017 being closer to the long-term mean. In other words, the effects were taking hold. So, seasonal thaw measurements at the Kramer's Field and Permafrost Tunnel sites. So they go through that. And then they look at the Farmer Loop sites. So let's take a look at these figures and what they're showing. They got these different colors. 2013 is represented in black, and that's the dry year, the driest year. And then we have 2017 in blue. So they have mixed forest, tussock tundra. Okay, they have here the active layer depth in centimeters. So this is a meter down. What we can see is that the active layer goes the deepest in the years where you had the most precipitation, because you had the warm water, it's liquid, so it's going to be warmer than freezing. It's starting to percolate down. It's starting to thaw the ground. It reaches further down. So in other words, the active layer, the seasonal thaw layer, which is the same, what active layer means, is lengthening. It's getting deeper. Right? It's fairly shallow compared to the other years for the driest year, 2013. That's what this is showing us. This is telling us that the rain is influencing and is starting to thaw the permafrost such that the active layer, the seasonal thaw layer, is getting deeper and deeper. That is the crux of this. That is your take-home message. We see that here as well. Okay. We see the same thing for the Farmer Loop sites here. The black 2013 is the driest. The seasonal thaw layer does not reach as deep as it does for the wet years. And there it is. Mixed forest shows the deepest penetration. And then another Farmer's Loop site, looking at the wetland, the mixed forest, we see the deepest penetration. But again, the pattern holds. The driest year, the seasonal thaw layer, basically was the shallowest whereas for the wet years, it got deeper. Disturbed areas, wetlands show the greatest absolute change in active layer depth, with basically 1 centimeter plus or minus 0.9 centimeters of additional active layer thaw per centimeter of rainfall. Then they look at the relationship between the active layer depth and the summer precipitation. So you can see linear regression here. Y is equal to, it should be y hat, the predicted value. This is a linear regression fit. 0.99 plus or minus 0.20x. Think about your old y equals mx plus b from high school algebra when you first learned about equations for straight lines. So this would be your m, your slope of the line, and this would be your intercept, and plus or minus 5.33. So this is an error range around the your slope value. This is an error range around your intercept. In statistical term, we would say y hat is equal to beta sub 0 plus beta sub 1x, where beta sub 0 is your y-intercept and beta sub 1 is your x coefficient. And so this would be the confidence interval, the errors around the respective parameters. As you can see, the highest slope is for the disturbed. The lowest is for the moss spruce forest. That's basically y equals 1,4x, or x over 4. So what do we have here? Okay, we have basically cat and whisker plots here. The box that you see here is the interquartile range. So that goes from the 25th to 75th percentile. The little line that you see there is the median. And then these represent the minimum and maximum values, called a five-number summary. So data categorized for 5 dominant ecotypes that vary in vegetation and soil properties, leading to variation in mean active layer depth, the variation in the y-intercepts. Okay? Box and whisker plots of thaw depth versus total summer precipitation are provided for the 5 major terrain types, okay? As we showed here. Upper and lower whisker lines denote the upper and lower 10% values, respectively. Box lines denote the upper 25%, the median and lower 25% values. Okay, that's basically saying the median is the 50th percentile. The lower 25% is the first quartile. The 50 plus 25 is 75. That's the 75th percentile. So 75 minus 25 is 50% of your data. And it's called the interquartile range. So when you see lower 25%, that's the 25th percentile. Upper 25% is the 75th percentile. The linear fit, the black line, that's this guy here, is provided. The grade area indicates the upper and lower 95% confidence interval. This is your error range. So total summer rainfall by ecotype interaction. P is less than 0.001. That is a significant result. And then the F value is 10.74, which is also a significant result. This is an ANOVA table, analysis of variance. We conduct an F test. An F statistic is computed. You compare it to the significant value for the levels and the degrees of freedom. And in this case here, I can tell you, looking at the values here, that is a significant result. So what this is doing, this is equating the thaw depth with the rainfall. And the fact that this is significant tells us that there is indeed a relationship. That's what this is telling us. So that when there's more precipitation, more wet precipitation, the thaw depth, the seasonal layer deepens. That means and it deepens the more so with more rainfall. So the rain is first of all, it's lasting longer, so we're getting more rain during the year, so its effects are going to be more pronounced. It's reaching further into the ground, percolating through, melting and thawing as it goes down, so that the thaw layer is deepening. This will influence what happens in this, in terms of methane release, i.e., more of it. And they show that there is significance here. And they go on to discuss the different types of ecosystem types and how they responded to these effects. And again, I will, for those of you who are interested, click on the link and you can read through the article here. But I wanted to discuss with you some other interesting aspects from the text. 4 of the summers in our measurement period were warmer than the 91-year mean summer temperatures, but only slightly. The lack of dependency between summer season thaw and winter precipitation, summer air temperatures, or the ice content of the seasonally thawed soil supports our interpretation that changes in active layer depths across our measurement period were driven predominantly by interannual variation in rainfall. Okay, that's their precipitation. I've given you my assessment of what the data is, to me, is indicating. The projected future wetter and warmer conditions across most of the Arctic will trigger shifts in vegetation cover and disturbance regimes, and this study demonstrates how land cover types govern relationships between summer precipitation and permafrost thaw. Human land use, roads, trails, infrastructure represents a much smaller proportion of disturbed landscape in the Arctic relative to wildfires which combust the thermally protective surface organic mat and vegetation, accelerate thermal karst and degradation of ice-rich permafrost. Our results suggest increasing areas of disturbed, deciduous, or open, unforested habitat could promote permafrost thaw under projected future wetter summer conditions. However, projecting how, where, and at what rate, and how this affects the thermal state of the permafrost will require better physics-based ecosystem models. Translation: more research, give us more funding so we can do the research. Part of that new more research will look at creating heat budgets and thermal energy budgets. Okay, so a brief discussion section follows. Following most disturbances of permafrost terrains, ice, massive ice with interstitial pore ice, and the permafrost melts and the volume change leads to ground surface subsidence. Spit it out. This in turn can lead to surface water inundation or shallow subsurface flow in low gradient locations. Basically, the ground is pretty flat, particularly in lowland landscapes. Our results suggest this process, along with increased summer precipitation, may cause a positive feedback to permafrost thaw and degradation. When permafrost degrades and the land subsides, this provides low-lying areas in which water can pond or pool and further thaw the permafrost soils. Usually what happens is when it rains, the water will accumulate on the surface for one of two reasons. The ground is so saturated it cannot absorb any more water, so the water starts pooling. And or, in the case of the Arctic, it can percolate through, but then it hits the permafrost, which is a barrier now, so now it cannot penetrate. Well, guess what? With the warming air temperatures and a longer wet precipitation season, and the water is itself, with the increased sensible heat content, is able to, it's warmer, so it's starting to penetrate further down into the ground, further thawing past the seasonal thaw layer, which would then, whatever thaws out will be added to the seasonal thaw layer, and the seasonal thaw layer is getting deeper and deeper. So this is what's happening. And they go on to discuss a few other implications of what's happening. And then here's they go into the methodology with telling how they do everything. Now, I did a video some time ago where I talked about how the extended rain season, the extended time from when rain instead of snow precipitates, how that is helping to melt Greenland's ice. So basically, I am now making the argument that we're seeing similar mechanisms. Extended wet precipitation, in case of Greenland leads to increased ice melt along with the warming air temperatures. Here in the Arctic, warming air temperatures leading to the permafrost thawing with the methane being released. Well, now we also have increased wet precipitation season with an increased sensible heat content of the rain itself that is further thawing the ground, which then deepens the thaw layer, adding to the thaw layer, and therefore further accelerating the thawing of the permafrost and the release of methane. So even if an Arctic region is not warm or it don't have a lot of sunshine, but if you have a lot of rain, the rain could just as easily be contributing to the thawing permafrost in addition to simply having warm, sunny skies. So we're seeing similar mechanisms at work, whether we're talking about the permafrost and terrestrial ecosystem or the great ice sheets on Greenland. Either way, between a warming air temperature and increased rain season with higher sensible heat content, both of these mechanisms are increasing the thawing of the permafrost, which then leads to increased methane into the atmosphere. That is the message I want you all to take from this study. Thank you for your time, and we'll talk soon. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.